What? I built my own asset manager for files or file manager. To manage the files. Like when you do file caching and to handling how the two things don't write to the same file to make file use handling easier just across programs. It is written in C++, just because you C++ and Python now. It can be linked like to Python. You can run C++ code from Python. So the pipeline just needs to be done for that eventually. This is the CMake. Make as part of the repo. For the FT minimum version, of course. And then the language, C++, the standard 23, version 23. They have the asset manager as a library, and we have the asset manager, the CPV implementation file and the declaration file are both here. Then we link target. We link the library of the asset manager. We link common lib onto it. That's a common library, and that thing exists. It's private link, so it doesn't propagate to targets that include the asset manager. If you want it, this must be public. Then you have here the asset manager. The target includes directory for the asset manager. It includes disk current source directory. So that includes disk directories. This is H files included with this target publicly, so it goes to each new target. Then we go to our implementation file. Here below is the implementation file. This is declaration file. This is basically the contract. If you include this, you can basically call these functions, and these functions are hidden in the CPP, the assets manager.cpp. First of all, here we have our file manager. This thing is not actually does the managing files. This is just 100. This is 100 lines of code. It's not that much. First of all, we have our open. First of all, we have we have four variables: a set, and 3 maps. Of which the first map is basically counting for absolute path. How many times it is open? So if you twice request a file with the same path, then it says then it stores true in the second location. And the second one is that caches the whole text file, and the third one is the whole binary file, and the fourth one is a set with all paths that have requested a write access to write to it to the file. Then there are 8 functions, and these functions are technically very simple. You can request a text handle, a binary handle, text write handle, binary write handle, and you can also return all of these. But you don't technically need to return them because there's something really useful about handle objects. The return function is called in their destructor. So as soon as they destruct, they return their own assets. They call that, and when that finishes, they actually get destructed with normal C++. Request the text file, and most often you will store this thing in the heap, and they store a a pointer to the data, so they can, if they're a write file, there must be alone, and there must be no readers, and so then they have a manipulatable version of the source. Like they point to a source without constant, else they point to a constant version of the source, and they contain manage themselves, and they have their own path. What path here? Of course, you can just save it to disk outside of the fact that you actually use it, but that will be a weird decision. Why would you go out of your way to save the disk when using file manager? Anyway, there are 4 types of handles. We have text files and binary files, and both have the write handle. Because the write handle, you can manipulate the data. So you can, for example, here each function that can error returns a result. This get can error, and so returns a result of the vector. It might give you an error, and here we can go now to the CPP file with the big important parts. First of all, this is the return binary write file. It's very simple. First of all, we can go over all the binary file functions. First, over the text file. First, let's go over the text file function. First of all, you give it a path, and the path is turned to the file manager. It's not an absolute path, because else you can have two HackerLamp files in two different directories. So we say, well, these are absolute. These are no longer different. The next step is basically, hey, this thing exists in write files. Hey, then it's in use. Then we return an error. Hey, then we can access custom data. Hey, if it's in here, if it's not in here, then read it from disk. Else take it from the cache. Then we get a number of times, and then we check if the assets, if it is in assets opened. Then if it contains it, then we get it from there, and then we say, hey, it's equal to it's equal to one more, and then we save it to the same place, and then afterwards we save in the text file the data to that place. The same happens with the binary file. Then we return a result of a text handle that has a pointer to the manager and an absolute version, and then we can, if we want to return it, we give again the path. We get absolute path, but it's important because that's where the text handle gets the manager, because it gets the manager when this thing is destructed. In the destructor, it calls this function. This thing runs on all that. It basically says, hey, if it's not in there, hey, then it doesn't exist. Then just return. If otherwise we get the amount of times it's opened, and then we if it's equal to 1, we erase it, because then it's no longer open. We just erase it and delete it from memory, and then else we decrease it by 1 and we just reassign it. That's the normal process. And of course, then there is the request write file. Write files work a little bit different. We again make it absolute. Then we check, hey, do our current file, is this file currently being written to? That's the second part here. If write files contains its absolute path, that's the second part. The first half is the assets that's opened. If it contains the absolute path, it's opened, like it's being read from. Then we also return here the error of error type file in use, and we return it. Well, else we do write files dot insert the absolute path, because then it isn't being written to. So we insert it in the write file. Well, then we read the whole path then we read it from data. And the next step is of course to go here. If it's not a file, then we return the file is not an error type. If the file is not found, of course the same result type, and then return it here. Else we read the file and return it with a manipulable instance, like a non-constant instance of this text file. And again, this thing has the manager, and so this text write handle destructor calls the return text write. In its destructor, it returns its asset, and it says, hey, we don't need this anymore. But here, this thing basically says, hey, make it absolute. If it isn't in there, we just, well, you can't return it. It is no longer in here. Also, really doesn't matter if it's not like in here. This might hide a bug, so we might need to change it a little bit, because I don't know if it, to me this doesn't yet. But you might hide a bug by the fact of saying, hey, we don't need to know if this path didn't exist, because that's just normal behavior, right? That's what always happens. You always don't find it anymore in there. Well, the next step is, hey, you erase it from the write files, from the assets opened, and from the text files. Then that's no longer in there, and then that's fully completed. And then you basically have returned the write file. For binary files, it happens the exact same way. And those are the returns. And that's basically it. We can go over one of these, and for example, text handle, we go up here. Hey, we reconstruct it. Hey, the manager, and we move the path, and we get the data. The data was a constant thing of a point, and that's also stored in here. You have the destructor. That if there's a manager, then we return the text file. The path. Here, this just reconstructs itself, moves it over. That's a move. Then we have here the equals operator. This is a move. And then we say, hey, if this is not equal to other, then we go, and then we do this, and then eventually we return this. And here you get it. You have a constant. This returns a constant string. You return the dereferencing of data. That's basically it. And then you go to the text right handle here below. So that's basically how it works. And yeah, it also uses the error type. It's basically, hey, you can return either data or an error, and that error can also have data inside that you can retrieve to get information about the error, and that's pretty useful.